In this video, we'll be going over separable differential equations. A separable differential equation is any differential equation that can be written in the form n of y times dy dx equals m of x. Now, the variables don't necessarily need to be x and y. In other words, we must be able to separate all of the one variable, or the y's, so that it's multiplied by the derivative, and all of the x's can be moved to the other side of the equal sign. And again, it doesn't necessarily have to be x's and y's. Those are just the variables that we're using here. In order to solve that type of differential equation, we would integrate both sides with respect to x to get the integral of n of y times dy dx times dx is equal to the integral of m of x dx. Remember that y is really y of x, and so we can use the substitution u equals y of x, which implies du equals y prime of x dx, which is the same thing as dy dx times dx. After applying this substitution, we would get the integral of n of u du is equal to the integral of m of x dx. At this point, we can hopefully integrate both sides and then back substitute for the u on the left side. Note that it might not actually be possible to evaluate one or both of the integrals at this point. If that's the case, then there won't be a lot we can do to proceed using this method to solve the differential equation. Now, the process above is the mathematically correct way of solving this differential equation. Note, however, that if we, quote, separate the derivative as well, we can write the differential equation as n of y dy equals m of x dx. If we integrate both sides, we get the integral of n of y dy equals the integral of m of x dx. And the reason that we're saying this is something that we emphasize: dy dx is not a fraction, and so that's not quite what we're doing, but we are separating it. This is exactly the same as the boxed equation above, just with the variable y instead of the variable u. In the interest of saving time, we will solve our separable differential equations in this quicker way. So let's go ahead and look at an example. Example 1 says find an explicit function that satisfies the following initial value problem: y prime of t equals y squared times e to the negative t, where y of 0 is equal to 1/2 for t greater than or equal to 0. Now, if you don't remember really quickly, this thing is called an initial condition. And we are given an initial condition so that we may solve for a particular solution. And another thing that I want to emphasize is it asks for an explicit function or an explicit solution, which means that we want our solution to be in the form y equals something. So let's go ahead and rewrite our differential equation. Instead of y primed, I'm going to rewrite it as dy dt equals y squared times e to the negative t. From here, what I want to do is we want to separate the variables. So I'm going to divide both sides by y squared. So I'm going to have 1 over y squared dy dt is equal to e to the negative t. And then I'm going to separate our derivative. So we have 1 over y squared dy is equal to e to the negative t dt. From here, I can integrate both sides, and the integral of the left-hand side would be negative 1 over y. And then on the right-hand side, if we integrate that, we get negative e to the negative t plus some constant of integration. Now, from here, what I'm going to do to get this into explicit form is I'm going to take the reciprocal of both sides. And if I do that, we get negative y equals 1 over negative e to the negative t plus c. From here, I'm going to multiply both sides by negative 1. And on the left side, that will give us y equals. And on the right side, I'm going to distribute the negative 1 that we're multiplying into the denominator. And so that's going to give me e to the negative t. And this is where students will sometimes get a little bit confused. There's multiple different ways I can deal with the constant. I could, because I'm distributing in a negative 1, I could write minus capital C, but C is just some arbitrary constant. And so really, if I'm multiplying it by -1, if I'm multiplying capital C by -1, it's just really going to give me plus some other constant that now I'm just calling C1. So I'm going to show you that both ways are fine, and both of these ways will get us the correct answer. So let's work with this one and then also work with this form. So y equals 1 over e to the -t minus c. So both of these will get us the correct answer. And both of these right now are the explicit solution in as a general solution, and we want the particular solution, so we're going to plug in our initial condition of y of 0 equals 1/2. So on this side, I'm going to replace y with 1/2, and I'm going to replace t with 0. And if we take the reciprocal of both sides, I get 2 equals e to the 0 plus c1. I know that e to the 0 is equivalent to 1, and so that's going to end up, if I subtract 1 from both sides, give me that c1 is equal to 1. So in this case here, again, I'm going to replace y with 1/2, and then we have 1 over e to the 0 minus c, and then if I take the reciprocal of both sides, e to the 0 is 1, and if I subtract 1 on both sides, then I get 1 equals -c, and then capital C equals -1. Now, even though we got different values of c, why is this giving us the same final answer? I've gone ahead and cleaned up the screen a little bit, but in this scenario where we found that c1 was equal to 1, if I replace that in my solution, I get y equals 1 over e to the -t plus 1. So there is my final answer. And in this scenario here, if I replace c with -1, that's going to be 1 over e to the -t minus -1, which turns into plus 1. So notice that that is the same answer that we got in the box over here. So regardless of how you want to work with your constant of integration, you should get the same answer either way you do it here. And so this concludes example 1. Example 2 says, explicitly solve the differential equation dy dx equals y over x for part A. So I'm going to go ahead and separate the variables, and if I divide both sides by y, and then move the dx over to the other side, we are here, and I'm going to integrate. So we get the natural log of the absolute value of y is equal to the natural log of the absolute value of x. And a student asked me in class today, on the left-hand side, why are we not adding a constant of integration? And if you want, you actually can. So what I was going to write was I was just going to add on a capital C here. But if you wanted to, you could also add it on the left side. So you could put plus, maybe I'll call it C1. But what's going to happen is if I subtracted C1 from both sides, capital C minus C1 is just some constant. And so it's unnecessary to put it on both sides because the constant is just going to get absorbed by the other constant. So I'm just going to go back to what we had originally, and I'm going to add on a constant, but actually I'm going to write it in a form that I think is going to make it a little bit easier for us. So I'm going to put plus and then the natural log of the absolute value of c, which is again just some arbitrary constant. Now, I did it because of the logarithm law that allows me to combine on the right-hand side those two natural logs into a single natural log, which turns into the natural log of the absolute value of cx. Now, from here, I could make both sides of the equation the exponent to e. And if I do that, then I'm going to end up getting the absolute value of y is equal to the absolute value of cx. And normally we get rid of absolute value bars by utilizing plus or minus. And again, c is just a constant. And so what I can do, I'll drop the absolute value bars and put plus or minus cx. And c is just a constant, and it could be positive or it could be negative. And so I'm going to rewrite this as y equals c1 times x, where c1 is just some constant that could be negative or could be positive. Now in part B, we're actually going to find out what that constant is. Part B says, find the solution of this differential equation that satisfies the initial condition y of 1 equals 7. So what I'm going to do is I'm going to take my general solution, replace y with 7, and replace x with 1. And that's going to imply that c1 is equal to 7. So our particular solution in explicit form will be y equals 7x. Example 3 says solve the differential equation x squared plus 1 times y prime equals x times y explicitly. So we have x squared plus 1 times dy dx is equal to x times y. So from here, I'm going to divide both sides by y and divide both sides by x squared plus 1. If we do that, we get 1 over y. Dy dx is equal to x over x squared plus 1. And then I'm also going to separate our derivative, so we get dy and dx on the other side. From here, I can integrate both sides, and I get the natural log of the absolute value of y is equal to, I'm going to use some u substitution on this. So I have u equals x squared plus 1, then du will equal 2x dx, and then we'll get 1/2 du is equal to x times dx. And then that will become 1/2 the integral of 1 over u du, which is equal to 1/2 times the natural log of the absolute value of u, which is x squared plus 1. And then we can put our constant of integration there. So on the right-hand side, we have 1/2 times the natural log of the absolute value of x squared plus 1 plus some constant. On the left-hand side, I'm going to rewrite that, just rewrite that natural log of absolute value of y equals. Now, based off one of the logarithm laws, I'm going to rewrite this as the natural log of the square root of x squared plus 1. I can bring the power inside, and x squared plus 1 to the 1/2 power is the same thing as the square root of x squared plus 1. And then, similar to last time, I'm going to take the natural log of c1 so that I can combine those, but actually that would be a different constant, so let's just call it the natural log of c2. So now we'll get the natural log of the absolute value of y equals, I'm going to combine those two natural logs on the right-hand side of our equation into the natural log of c2 times the square root of x squared plus 1. And then if I e both sides, I'm going to end up getting the absolute value of y is equal to c2 times the square root of x squared plus 1, and I can drop the absolute value bars, and the constant on the other side, if I put plus or minus, will just absorb the plus or minus, and I'm just going to rewrite it as some constant, capital C. And here is our final answer for example 3. Example 4 says explicitly solve the differential equation du dt equals 2 plus 2u plus t times u. Now, there's 4 terms here. Let's see if I can factor out in the first 2 terms. I'm going to factor out a 2, and that's going to leave me with 1 plus u. And in the second two terms, I'm going to factor out a t, and that's also going to give me 1 plus u. And then from there, we can factor out 1 plus u, and we'll be left with 2 plus t. So now what we can do is separate this. So I have du dt is equal to 1 plus u times 2 plus t. And I'm going to divide both sides by 1 plus u. So I'm going to get 1 over 1 plus u du. And then I'm going to move the dt to the other side. So I have 2 plus t dt. From here, I'm going to integrate both sides. All right, if I integrate the left-hand side, that's going to give me the natural log of the absolute value of, I'm going to switch the order, so u plus 1 is equal to, then we have 2t plus t squared over 2 plus our constant of integration. From here, I'm going to e both sides, and then on the left side, we're left with the absolute value of u plus 1 is equal to e to the power of 2t plus t squared over 2 plus c1. Now, here's what I'm going to do. This is equivalent to e to the c1 times e to the 2t plus t squared over 2. And the reason that I'm doing that is because now in the front, I'm multiplying by some arbitrary constant. E is a constant, and if I raise that to a constant, then we have a constant. So at this point in time, let's clean this up. We have the absolute value of u plus 1 is equal to e to the power of c1 times e to the power of 2t plus t squared over 2. At this stage, I'm going to drop the absolute value bars and put plus or minus e to the c1 times e to the 2t plus t squared over 2. And this thing in front here is just some constant. And so I'm just going to replace that with a capital C, and I'm also going to subtract 1 on both sides of the equation. So I end up getting u is equal to capital C, which is some arbitrary constant. And then we've subtracted 1, so there is our final answer for example 4. Example 5 says, explicitly solve the following initial value problems. So in part A, I'm going to divide both sides by y squared plus 1, and then move dx to the other side of the equation. And, oh, I forgot the dy. And if you want, you could put 1 times dx so that when we integrate both sides now, the antiderivative of 1 over y squared plus 1 on the left-hand side will give us arctangent of y is equal to x plus some constant. And then from here, we want to explicitly solve for y, so I'm going to apply tangent to both sides. So we're going to get y equals tangent of x plus our constant. All right, so now we're going to plug in our initial condition. We have 0 equals tangent of 1 plus c, and tangent equals 0 at many different locations since tangent is a periodic function. So I'm just going to think about the case where tangent of 0 is 0 at 0. So that would mean that c plus 1 is equal to 0 and c equals negative 1. And so we get y equals tangent of x minus 1. But again, there's actually infinitely many values for c. I'm just going to stick with this. For part B, we have dp dt equals the square root of p times t. And because of square root properties, I can rewrite this as the square root of p times the square root of t. And if I divide both sides by the square root of p, we get 1 over the square root of p dp equals the square root of t dt. And I'm going to integrate both sides. It'd probably be helpful to rewrite these as p to the negative 1/2 and t to the 1/2 so that we can end up using the power rule for integrals. So I'm going to increase the power by 1, divide by that new power, and then we have t to the 3/2, and then dividing by 3/2 or multiplying by the reciprocal, and then plus our constant of integration. From here, I'm going to divide both sides by 2, and if I do that, I get p to the 1/2 is equal to 1/3 t to the 3/2 plus, if I take my constant c1 and cut it in half, that is just going to give me some other constant. So I'm going to call that c2. From here, in order to get the explicit solution, I'm going to square both sides. So we get 1/3 t to the 3/2 plus our constant of integration squared. And then we can plug in our initial condition. And t becomes 0. So we are left with that. And then if I solve this for c2, by taking the square root of both sides, I get c2 is equal to plus or minus root 2. And so we end up getting p is equal to 1/3 t to the 3/2 power plus or minus the square root of 2 quantity squared. And here is our final answer. All right, for part C, we have x times y prime I'm going to replace with dy dx plus y equals x squared. So I'd like you to take a moment and think about what do we do here and how do we go about solving this. So go ahead and take a minute to pause the video and think about how we could rewrite this. It turns out that this is not an example of a separable differential equation because we cannot get it into the form n of y dy equals m of x dx. So this is just an example to show that not all differential equations are separable, and so we cannot continue on with this because we don't know how to solve this kind of differential equation. Example 6 says a curve passes through the point 4, 2 and has the property that the slope of the curve at every point P is 3 times the y-coordinate of P. What is the equation of the curve? So based on the information that's given, we can actually set up a differential equation and an initial condition. So it says that the slope of the curve or the slope of the tangent line at every point P is 3 times the y-coordinate of P, which is another way of saying dy dx is equal to 3 times the y-coordinate. And then if we know that the solution curve goes through the point 4, 2, that is giving us the initial condition that y of 4 is equal to 2. So let's go ahead and separate this. I'm going to get 1 over y dy is equal to 3 dx. And if we integrate, we're going to get the natural log of the absolute value of y is equal to 3x plus our constant of integration. Then if I e both sides, I'm going to get the absolute value of y is equal to e to the 3x plus our constant of integration. And I'm going to rewrite this as the absolute value of y is equal to e to the c times e to the 3x. If I drop the absolute value bars, I get y equals plus or minus e to the c times e to the 3x. And plus or minus e to the c is just some constant. So maybe I'll call this c1 now. And then we have our initial condition. So I'm going to replace 2 or y with 2. And I'm going to replace x with 4. So we get C1 is equal to 2 over e to the 12th power. So if I replace C1 with the thing that we just found, we're going to get y equals 2 over e to the 12th times e to the 3x. And just to do something kind of slick, this is the same thing as 2 times e to the 3x over e to the 12th. And so that I don't have to deal with a fraction, that's equivalent to 2 times e to the 3x minus 12 because of the way that exponent properties work. And so here we have our final answer. Example 7 says, for what values of k does the function y equals cosine of k times t satisfy the differential equation 9 times y double prime is equal to negative 25y? So we have y equals cosine of kt. I'm going to go ahead and solve for y prime, which ends up being, if I use chain rule, negative k times sine of kt. And then if I take the second derivative, that's going to give us negative k squared cosine of kt. And so now what I want to do is I want to plug those values into our differential equation. So I have 9 times negative k squared, so I'm going to write it this way, is equal to negative 25, and then our y value in this case is cosine of kt, and I'm just going to compare the coefficients because cosine of kt and cosine of kt, so their coefficients should be equal. So we have negative 9k squared is equal to negative 25. If I divide both sides by negative 9, I'm going to get 25 over 9. And then if we take the square root of both sides, we get k is equal to plus or minus 5/3. So it just asks for what values of k. So here are our k values, and that's our final answer for example 7. Example 8 says solve the differential equation dy dx is equal to 3x squared over 2y plus cosecant squared y. And this is a separable differential equation, so I'm going to rewrite this as 2y plus cosecant squared y. And then this is all being multiplied by dy, and then on the right hand side we have 3x squared times dx. From here, if we integrate both sides, then on the left-hand side, we're going to have y squared minus cotangent of y is equal to x cubed plus our constant of integration. And notice that this example did not ask us to solve this explicitly. And in this case, it's because we cannot do so. We cannot isolate y in this case, so this is our general solution to this differential equation. So in the purple box below, you can read that it says something important to note is that we are not always able to put solutions to differential equations in explicit form. In these instances, we leave our answer in implicit form. So that concludes this video on separable differential equations.